Hello, welcome, and we are glad to have you all for part one in what will be a three-part series about mastering aerial LiDAR. So obviously, for those of you that don't know me, my name's Logan. I'm the founder and CEO of Aerotas, and today we're going to be talking about the entire LiDAR ecosystem. This is not quite an intro to LiDAR because we'll go a little bit more deep than that, but we're going to talk about aerial LiDAR, particularly drone aerial LiDAR, what it looks like today, what it's going to look like in the future, and where it all came from. So with that, let me get the right tabs up so that I can get started. So what I want to cover with everyone today is we're going to talk about an overview of basically the entire aerial LiDAR for drone surveying. Now, I just want to be clear with a couple of people. If you registered and were expecting something else, this is primarily a drone LiDAR class. That's what we're going to be talking about. LiDAR is a technology that can be used for so many different things, but drone LiDAR for surveying applications is the primary thing that we're going to be covering today. So we're going to start with a couple fundamentals. I am a tech geek myself, and I think it's actually really important to understand at least the basic fundamentals of how a technology works, because that can really help inform us how it can be used effectively, how it's going to change in the future, and honestly, how it shouldn't be used. So I want to make sure that we're all on the same page of actually how LiDAR technology works. Then we're going to dive into a little bit of a political hot button issue, which is drone hardware in 2025. What's the best hardware? What's available? And honestly, how are tariffs and geopolitical tensions impacting supply and supply chain issues and prices and all of that? Because that's very hard to keep track of. And that's, one of our main jobs that we do here. And we still struggle keeping track of everything. We're also going to talk about LiDAR and photogrammetry a lot and the choices between those two. While this is a map or a talk focusing on aerial LiDAR, drone surveying for the last 10 years or so has been dominated more by photogrammetry. And there are some reasons behind that, but how does LiDAR and photogrammetry stack up against one another? Is one universally better, and where do we go from there? And then we're going to go over the basics of data processing, what a data processing workflow actually looks like, what the different steps are to go from actually flying a LiDAR drone and getting into final things. Those are what we're covering. And now I should point out, this is part one of a three-part series, so we'll talk a little bit more about that later. Part two, we're going to cover a lot more about the actual business case for LiDAR. The business case being, how do you make money? How does it work for different businesses? How do you make sure that your workflows are efficient to actually turn this into a business application, not a research program? And then part three of our three-part series will focus way, way, way more in depth on the data processing, much more about the data, actual examples, and that sort of thing. And a little bit about us and where this presentation comes from. I know I see a bunch of our existing clients are on this as well. But at Aerotas, we do drone data processing for surveyors, and we've been doing it for over 10 years now. Customers all over the US have rely on us to actually process their LiDAR data. And this isn't a sales pitch as much as it is to say, this is the source of this information. The reason why we have the ability to give these sorts of presentations is because we've processed tens of thousands of data sets and tens of thousands of LiDAR data sets at this point. So we actually get to see what works, what doesn't, what are good practices, what are bad practices, and how to actually be successful as a company using LiDAR and surveying. Because I'll tell you, my perspective about LiDAR surveying and all surveying in general really is our goal is to help you build a program that saves time, saves money, gets you better deliverables. And honestly, if it's not doing all of those, then it isn't working. This is very much my philosophy that the point of this presentation is not to help you build a research program. It is to help you build a business. And a business is not about, testing things one time. It's about building a repeatable workflow. And another theme that you're going to hear me hit on a lot, which is actually really tricky for a lot of surveyors, is the theme of finding balance. The reason I bring this up is because you have to find balance in order to be a successful business. You have to find balance between things like accuracy, efficiency, speed, reliability, and cost. This is a really important perspective for me because, and it's actually been cropping up in a lot of things in my life where it's so easy to come into a thing like a drone program or any sort of technology and say, all I care about is accuracy. Everything else doesn't matter. Accuracy is the only thing that matters, blah, blah, blah. And you wind up having a drone program that's way too expensive. It takes way too much time. You try and charge too much money. Your clients never use it, and it just no longer works. So it's easy to try and be ideologically pure and say, all I care about is making the cheapest program available, or all I care about is accuracy. But really, you've got to take the messy questions, the messy trade-offs to find balance. And everyone will find a different balance that's right for your business, and that's okay. But the method I want to point out is that I do not come from a science background where accuracy and pure technological perfection comes at any cost, because quite frankly, none of us have $100 million budgets, as cool as that would be. So my goal is to help you find balance to actually get to a final map, to a final deliverable. And again, that is what Aerotas does. If you're interested, we'll have some links at the end if you want to work with us, but this isn't a sales pitch. This is very much a technical, deep dive technical webinar. But of course, if you do want help processing your LiDAR data, that's what Aerotas does. We have a number of different deliverables, from photogrammetry processing, topo mapping, and LiDAR deliverables, all of that sort of stuff. But I don't want to get too much into what we do, and rather into how we can help you and your companies build a map. Because we're talking about drone LiDARs and drone LiDAR surveying, and a lot of people really enjoy being on the drone side of things. They want to be the pilot. They want to buy the cool drone, and they want to have a good flight. But I always like to remind people that the end goal of a drone surveying program is not a flight. It is not a successful flight. That is an intermediate product. The end goal is to get a map that is accurate, that is what the client needs, that is at an appropriate speed and an appropriate cost, and balancing all of those things. So that is the end goal. That is what we are laser focused on, is how do we go from getting LiDAR data using this admittedly awesome technology and getting to a map. So let's start with the LiDAR fundamentals. And again, some of you probably know this pretty well, but I think it's really important to start from the first principles, from the basics of how LiDAR works, to inform us when it can, when it should, and when it can profitably and successfully be used. So LiDAR basics. LiDAR itself stands for light detection and ranging. And it's funny, I've noticed people capitalize LiDAR very, very differently, either in all caps or in lower caps as a common noun, or capital L, lowercase I, because it comes from lights, and then DAR, detection and ranging. There are a whole bunch of things, and I'm not going to quibble about it, but I found some engineering group that decided to formally adopt that LiDAR is a common noun and should be capitalized only at the beginning of a sentence, and otherwise it's all lowercase. Not that that matters at all in what we're doing. Light detection and ranging. What LiDAR does, LiDAR is a laser that sends out hundreds of thousands of laser pulses per second, and it records the angle and distance coming back to it. Each pulse precisely measures the angle and distance and brightness, also known as intensity, coming back into it, and it can measure multiple returns for things like vegetation as it sees different things. It is worth noting LiDAR uses a wavelength that is invisible to the human eye, and it is not colorized, which means that LiDAR cannot see color. It is fully uncolored, and it also, LiDAR is not dangerous to human eyes. It's part of why we can put it on a drone, fly it over people, and if it were to hit someone directly in the eye, it does not actually cause any damage whatsoever. The laser itself is a wavelength that is opaque to the human eye as well, so it can't actually harm the eyes at all. And typically, once we actually get this raw LiDAR data, it is combined with other sensors to create a proper point cloud. The laser scanner is only a single part of the system. It's combined with the IMU, or inertial measurement unit data, the GNSS, GPS, RTK data, that sort of thing, as well as a number of other things. So it's combined together to create a proper point cloud. And then I also I'll go over very briefly, a history of LiDAR, because this comes from me being a tech nerd. I'll go over where LiDAR actually came from. So laser range finding, the fundamental science of LiDAR, actually was developed in the 1960s. Hugely impractical, single point measurements, really heavy, really expensive, not commonly used, but the fundamental technology behind laser range finding is quite old, actually. Aerial LiDAR itself was first tested in the 1990s, And then it was expanded a lot in the cultural zeitgeist when some aerial LiDAR fixed wing based, very heavy, very expensive, very low resolution by modern standards. Aerial LiDAR helped to discover Mayan ruins underneath forests in Central and South America in the early 2000s. LiDAR's first somewhat practical drone use started about 10 years ago, in about 2015, when companies like Regal started strapping very, very, very expensive laser scanners to drones. And it really grew massively with the DJI L1, which was the first easy to use and cost-effective drone in the year 2020, that's kind of a while ago. DJI L1 is still a fully functional sensor today, for being 5 years old. And I should point out another piece of history that I really love behind this. The reason that costs have come down so much in LiDAR is because of autonomous driving. Companies like Google via Waymo have put in billions of dollars of research and development into LiDAR technology to make it smaller, better, more readily available, lower power consumption, higher range, that sort of thing. So basically every LiDAR sensor that is on a drone today is a direct descendant of the research and development done by automotive technology. So just a fun little piece of technology history. That's where a lot of that comes from. But enough on history. Let's get into it. One of the primary reasons why people use LiDAR is for vegetation penetration. That is one of the biggest benefits of using LiDAR for survey. So I want to talk really quickly about exactly how that works. For starters, vegetation penetration comes from the laser itself finding gaps in the leaves. If you look at this little tree right here, this is what it would look like from the ground looking up through dense foliage, and you can still see little gaps of sky. The short answer is the laser finds those gaps through its hundreds of thousands of pulses per second, and it can actually see through to the ground. The laser, common to popular belief, LiDAR sensors or lasers cannot actually go through leaves. They don't actually penetrate anything or see through anything. They're just such a dense cloud of laser pulses that it's able to find the gaps. There are still, because of that, there are still some extremely dense vegetation types that will completely block LiDAR sensors, either in more tropical areas where you have very, very broad leaves and multiple canopies, that can do it, or in other places where really, really dense kudzu or something can fully block the ground completely. That does exist because, again, the laser can't actually see through the leaves. It just finds the gaps. If there are no gaps to be found, then it can't find the ground. Another thing with lasers and vegetation is low grasses. I'll cover this at excruciating detail in part 3 when we go through processing data with things like low grasses. But LiDAR, any sort of aerial scanner, does struggle with low grasses. That like 1 foot or 2 feet of very dense grass. The LiDAR sensors typically have a lot of trouble finding a true ground in something where the grass just gets denser and denser and denser as it gets lower and lower. So, and also another limitation of LiDAR, just to throw out some other popular beliefs, LiDAR cannot penetrate water, snow, eaves, or any other obstruction that would block light. Again, LiDAR doesn't actually go through anything. It just finds the gaps in it. I should acknowledge there are some very specialized LiDARs that can penetrate water. There's bathymetric LiDAR. That is a completely fundamentally different technology and also totally out of scope of what we're talking about today because you need different wavelengths of light, different lasers. It's just a completely different technology, really. The next question that I want to cover in terms of the fundamentals is aerial LiDAR accuracy. How accurate is aerial LiDAR survey? Well, typically they are accurate to around 1/10 of a foot. And very high-end or expensive systems can approach about 5/100ths of a foot, which is really good. I say more high-end just to make sure we're all in the ballpark. When I say high-end, I typically mean in the $100,000 to $150,000 per system setup. So they're quite, well, depends on your perspective. They're expensive systems, but you can get about 5/100ths of a foot for the more expensive systems. If you expect about 1/10 of a foot, then you can do that with more mid-range and entry-level LiDAR surveying systems. But for some people that are used to different LiDAR, like ground-based or terrestrial LiDAR technologies, that might not seem very good. And that's for a couple of reasons. One, I like to talk about how accuracy should be measured at the end of the survey here. So on the right is a copy or a picture of the ASPRS positional accuracy standards for digital geospatial data, which is a mouthful. I have other webinars and talks on accuracy that we can cover later. But basically, the idea is you measure your accuracy at the end of a survey. And with a LiDAR survey or any drone survey, error actually comes from a lot of sources, starting from the laser itself and the sensor calibration, scan angle and timing, your GPS errors, IMU errors, trajectory solution, point cloud processing, rasterization, blah, blah, blah. And this is why aerial LiDAR just fundamentally is not as accurate right now as ground-based LiDAR. Ground-based LiDAR is typically on a tripod, or even vehicle-borne LiDAR is going to be mounted on something on the ground, not that is moving, kicking in the air. There are a lot of different sources of error. So it's worth noting the laser itself is almost never the source of error. So people say, oh, this laser is accurate to 3 micrometers of distance. And it's like, yeah, the laser itself is. The error typically comes from elsewhere in the process. And the goal of a LiDAR survey is finding the total error. So as we're talking about that difference, aerial versus terrestrial LiDAR, just to cover a couple difference and misconceptions, because some people think that aerial LiDAR will get them a point cloud that looks exactly like their ground-based LiDAR scanner or a mobile LiDAR scanner, and that is not the case right now. As a rule of thumb, and again, there are plenty of exceptions to this, aerial LiDAR is about 1/10 of a foot accurate. You can get a little bit better, yes, but its benefits are it covers very, very large areas. And there are some challenges as well. It is power and weight limited. You can't strap a $2 million 100-pound LiDAR sensor on a drone, although there are fixed-wing aircraft that can carry those. And it's outdoor only. Terrestrial LiDAR is typically more accurate to around 3/100ths of a foot. It's, again, can exceed that. It can be better than 3/100ths of a foot, but it covers much smaller areas of a time. It has few physical constraints in terms of power or weight or something like that. You can put a much heavier sensor on, and it works inside. Now, there are enough differences, by the way, that I can tell you on the hardware side. Some vendors want to sell a single LiDAR sensor that you can strap to a drone, and then you can put it on a backpack, and then you can put it on a tripod. In our experience, while those are possible and they can save some money, we usually discourage it. It's not that the data is necessarily bad, but it's one of those jack of all trades is master of none sort of circumstances. The type of equipment needed to be successful on a drone really needs to, again, balance. There's that word again that I'm going to use a lot. Balance things like the power of the laser, the battery, the distance that it can cover. They're just different needs. So we generally discourage people trying to buy a jack of all trades LiDAR sensor, strap it to a drone here, a car there, an ATV, a backpack, and then put it on a tripod. It usually winds up being a pretty clunky solution overall, but we'll talk about hardware in just a little bit. Another big question about LiDAR is talking about the difference between photogrammetry and LiDAR. So what I always start with here, and we'll get into the details of photogrammetry and LiDAR in just a little bit, starting with achievable accuracy. Both of them, both photogrammetry and LiDAR, have achievable accuracies between 5/100ths of a foot and 1/10 of a foot. And by the way, I want to apologize. I know there are a handful of international people or students on here. I work in US surveying, and we work in hundredths and tenths of feet, not in centimeters, not in millimeters. I understand I'm not going to go through a whole spiel of metric versus imperial units or anything like that, other than to say in the world of US survey, we speak in tenths and hundredths, and ergo, that is what I speak in. All right, continuing on, photogrammetry versus LiDAR. Equipment cost. Photogrammetry is way, way, way cheaper. There's absolutely no way around that. Ease of use. Because it is cheaper, it is smaller, it is generally simpler, and it is generally easier to use than LiDAR. It is also a less complex system. You need fewer components, which means there are fewer things that can go wrong. And photogrammetry remains much better. It remains better than LiDAR at 2D feature identification. Where LiDAR really, really shines is number one, vegetation penetration, actually creating good ground and topo surfaces in vegetated areas, as well as power line mapping, which basically requires LiDAR. Photogrammetry cannot successfully or reliably do power line mapping or any towers or assets like that. So Because of this, LiDAR is just not appropriate for all surveyors and all projects. And that's okay. If 98% of your projects can be done with photogrammetry, it makes a lot more sense to have a $10,000 drone that you can fly anywhere because they're small, they're easy to use, they fit in a briefcase, they're just less intimidating, rather than to buy an expensive LiDAR one. For many projects, photogrammetry is not only cheaper, it is better. If there is no vegetation and no power lines, photogrammetry is a better solution. It is cheaper, faster, easier processing. But for a lot of them, flying a project with both photogrammetry and LiDAR simultaneously is a great solution. And we actually strongly recommend this. If you have a LiDAR drone, you should be collecting photogrammetry and LiDAR at the same time. So why should you use LiDAR for surveying, though? Topo and vegetated areas, power line mapping, those are the big ones. If you need topo, if you need to be able to get data underneath trees, underneath vegetation, then LiDAR is a very, very good solution. But for, I'd say most, that is changing. For many projects, photogrammetry is still cheaper and more accurate. And for a LiDAR talk, this is actually, I'm going to spend one slide at least on why you shouldn't use LiDAR, because LiDAR isn't right for everyone. And to jump ahead to the business side, one of the most important things in being successful with a new technology is knowing when it's the wrong tool for the job. LiDAR is incredible. We're huge LiDAR proponents. We love it, but it is not the right tool for every job. The hardware is very expensive, and a lot of businesses have gotten burned spending money on hardware that they aren't going to get enough use out of. LiDAR drones are bulky and harder to fly. We are not a company that makes our business by going out and flying, but we have a bunch of drones that we use for testing purposes. And I can tell you, our pilots almost always prefer to fly a photogrammetry drone if they can get away with it. It's smaller, no one asks questions. It's a single box that you have to throw in the truck. LiDAR drones, they take a lot longer to set up. They're heavier. Just the people in the field don't like using them as much. They're a little bit more of a pain. Photogrammetry is easier. It gets done a lot more. So we like it. 2D accuracy is lower than photogrammetry, which is why we typically use a blended workflow. I'll cover that in the data processing section. And generally speaking, processing takes more time. That's a little bit of a interesting statement because processing on LiDAR data by itself can be faster, at least in certain aspects, slower in others. It depends on your workflow, which we will cover in a little bit. But for now, I want to make the transition to actually picking LiDAR hardware. What does the LiDAR hardware ecosystem look like? Where do you go with it? So for starters, I'm going to start with my principles, how to pick a good LiDAR drone, letting you know at least where I come from. Number one, there is no best drone for everyone. I have my favorites, which you'll hear about in a second, but there is no best drone for everyone or for every business. People have different levels of skill, different budgets, different projects, project types that they need, and different requirements from their clients even. So there are numerous options available. Drones can be unique to individual companies, needs, and operators, but I will say there definitely are some bad drones and a lot of pitfalls for how you use them. My focus, again, is finding balance on drones for business purposes, not for research, not for trying to push the absolute cutting edge of technology on research programs. And so I say, don't make your drone program into a science experiment, which is something that I definitely did. I love finding this picture of me, by the way, that this is one of the only photos of me with one of my hand-built drones back in, that would have been 2013 or 2014 or so. And it took a long time for Aerotas to come from that kind of research program into a business today. And I can tell you, well, that drone actually crashed too. So don't do a research program. You don't want to crash drones. This is about business. So as we get into how we evaluate drones, like I said, it is balance. It is balance of a lot of things. Balance between accuracy, which matters but is not the only thing, about total cost of ownership, which, by the way, we evaluate as the cost of the equipment, as well as what it costs to operate and what the data processing costs. There are some drones that require a team of 2 people to operate them, and you cannot put them in the hands of anyone that isn't an extraordinarily trained and experienced pilot. That means the cost of labor and the cost of in that case, the cost of labor far exceeds the cost of the drone itself. We'll cover that in the business case scenario as well a little bit more. As well as the cost of data processing. Some are more expensive to data, or more expensive and time consuming to process data. So ease of use, hardware and software support, all of that. And at the end of the day, here's where we start getting into some of the political side of things too. There is just no question right now that DJI, as a hardware manufacturer, they are the market leader. They make the best drones available today on balance. Do they make the ones with the single best accuracy in the world? No, they don't. Do they make the drones that are the cheapest and simplest and easiest to fly? Not necessarily. They make the drones that on balance have very good accuracy, very good reliability, very easy to use. They are on balance the best drones out there, unless you want to maximize a single thing or you have other constraints, because there are some challenges. But I always you just kind of being honest, I just say how it is. Any non-DJI drone will have significant trade-offs relative to DJI. They are typically much harder to use. They often have fewer features. They are almost always more expensive, although that's changing a little bit in the tariff world. Sometimes they have worse accuracy too. And if you can, I always say you should be using a DJI drone. Now, this does get tricky because DJI is a Chinese company. They are subject to tariffs, and that means their prices have gone up an awful lot lately. So let's jump into it, though. DJI, their main hardware, which quite frankly is our favorite, we see overall on balance, we see a lot of our customers using this a ton. The M350 drone and the L2 sensor. LiDAR and photogrammetry simultaneously, which is the workflow we prefer. We prefer, if you are going to fly LiDAR, fly it in a single flight with LiDAR and photogrammetry simultaneously. This drone, as well as numerous others, can do that. Fully integrated, easiest to use, and pricing update. As of 4/29, yesterday when I updated this, though it seems to change, not seems to, it definitely changes about daily, the full kit cost of a DJI M350 is about $66,000. As of a month ago, it was about $36,000. The tariffs have really, really hit DJI drones hard. So DJI drones are generally available right now, the M350 and the L2. They are just very, very expensive because of the tariffs that are there. And this is as of 4/29. This could change really quickly. So just so you're aware, the drone itself now costs about $20,000. The L2 sensor costs about $26,000. And then all of the other stuff you need, whether it's base stations, cases, batteries, battery charging kit, accessories, yada, 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 all of that together is about another $20,000. So that's why I don't try and, bait and switch with, oh, buy the L2, it's only $26,000, and then you see a $66,000 price tag or anything. But it's the best drone overall. So let's actually acknowledge then, drones in China, this is a tricky and political issue right now. Again, I'm just stating the facts. There's no way around it. China designs and manufactures most commercial drones. I believe DJI at last check had about 70 to 90% of the commercial drone market. US tariffs have made DJI drones considerably more difficult, but they are still there and they are still available. They're just more expensive. Interestingly, at 66 grand, they're not that much. They're still on the cheaper side of a lot of American alternatives. As of right now, there are no restrictions, federal or otherwise, besides the usual Part 107 rules on DJI drones. But some entities might make their own rules. There are some states or state organizations or Department of Transportations that might say no DJI drones or something like that. And so I always get the question, okay, this is great, but why aren't there more US-made drones? What are the US-made alternatives? Well, the short answer is, why aren't there more US-made drones? There are, but they don't target commercial applications right now. US-made drones and drone companies and manufacturers are primarily targeting military and law enforcement and some first responder industries, but they are just not targeting survey yet. There are a handful of companies building for things like this, but if I'm just being brutally honest, right now, they are behind DJI when it comes to the balance of cost and technology and ease of use and reliability and payload integration and all of that stuff. So the kind of three main alternatives to DJI, at least in the LiDAR capable non-Chinese made drone category, are Inspired Flight makes one. That picture in the bottom right is the Inspired Flight IF800. There's the Wingter 1, which is a fixed wing hybrid VTOL. It's made in Switzerland, I believe, and Freefly makes one as well. But they're hard to recommend. They are not fully competitive with DJI yet, but they do have the advantage. They are going to be outside of the Chinese ecosystem, which is really big. Well, we're talking about DJI versus everyone else, because again, you just have any talk on hardware, it's DJI and everyone else. DJI is 70, 90% of the market. All of the rest of these drones sell like massively lower volumes of drones, and it's just hard to technologically support lower volume products. There are a million different companies out there. So here is, again, a very incomplete list of other non-DJI drones that are out there. There are tons of bespoke manufacturers. I'm probably familiar with at least 20 or 30 of them, and I know there are more. Before questions come in, oh, why didn't you mention X, Y, or Z? Look, I can't mention everything, especially when there are a lot that only build maybe a dozen drones that they sell per year versus DJI, which will sell tens of thousands and that sort of things. But that said, there are plenty of people successfully using non-DJI drone LiDAR systems. The reason that it is less common is because it is, one, expensive, and two, complex. Because typically there are kind of three components, and a lot of companies try and put these together, that need to work. One, you need the actual LiDAR sensor itself. These are companies like Velodyne, Regal, Livox, Quanergy, and Hesai that actually make the drone sensors themselves. One of the challenges here, even a lot of quote unquote American companies or non-Chinese companies actually are still using Chinese manufactured LiDAR sensors in there, like Hesai and Livox are both Chinese manufactured and that sort of thing. And then the LiDAR sensor itself gets integrated into a payload. Companies like Wingtra, GeoQ, Rock Robotic, LiDAR USA, Phoenix LiDAR, they actually make the LiDAR drones themselves. Oh, I just got a question on there. What's the best DoD or NDAA compliant non-DJI drone? That's a really, really, really tricky question because of this slide right here. You need the LiDAR sensor, the payload integration, and then you need the airframe itself. A lot of times people will put non-DJI payloads onto a DJI airframe, or the other way around, people might buy a DoD or NDAA compliant drone and then put a non-NDAA compliant or DoD blue list, or now there's the new DoD green, or there's the new UAV green list, which is various specifications that go on it. The short answer is it's really expensive to build a true NDAA compliant system because you cannot use a Chinese LiDAR sensor even if you put it on a fully American drone. Basically, you need to go through, I would say, probably a GeoQ payload, but GeoQ has some of their sensors that use Chinese sensors as well. So a GeoQ payload with either a Velodyne or a Regal sensor and mounted on something like a FreeFly Alta or a FreeFly Airs or something like that. But that's probably the best bet, but that's going to be wildly expensive and extraordinarily complex and require an enormous amount of training. So if you want to go full NDAA compliant, you better have a big budget is the answer. It's doable, but it's very, very expensive. So yeah, getting in here, these are probably the three biggest ones: the Inspired Flight, IF800, Microdrones EZ1, and the FreeFly Astro. I forget if the I forget which of these are fully NDAA compliant. I think all three of them are, depending on the payload that you put on. They all compete for the same class of drone, LiDAR capable as the DJI M350, but they require that payload integration. They are definitely way, way, way more expensive, and they are more difficult to use. And I really want to point out this more difficult to use, when we get to this idea of balance, is a challenging thing that a lot of people, particularly if you're on this webinar with me, you are likely going to be more educated and sophisticated than the average drone user out there, which, congratulations, there you go. My goal is to help you be more educated and sophisticated. And so if you're watching this, you think, oh, more easy to use, I'm really technical, I can actually get it done. But the problem is, when we get to the business side, when we get to that balance side, a drone can't be so complex, or in my opinion, it's a big problem if it's such a complex system that it requires a week-long in-person training to be able to understand how to fly it. Because then you, the technologically capable person, are the only person that can do it. And for a business case, your time is probably better spent elsewhere rather than just setting up a drone, pushing go and letting it autonomously fly, which is what DJI has been so successful at. They've been so successful that people regularly buy DJI LiDAR drones and give them to kids who are just starting out their professional career in their early 20s and say, here's a map, push, go, fly it. And they don't worry about a $60,000 LiDAR system because it's really reliable. Whereas a lot of these systems are, I've talked to some of the hardware manufacturers too. I've heard one of them say that their goal is to build a pilot-centric drone or a pilot-forward drone. They think of it the pilot first. And I sit here being on the data side, I'm like, the data and business side, and thinking like, that's terrible. I don't want a pilot first drone. I want a drone that flies itself autonomously. Pilots make mistakes all over the place. These are drones. This is not a 737 where you want a pilot. This is where you want a computer to take over and actually go there. A anonymous question. Someone just bought the IF 800 and does not recommend it. So FreeFly Astro or Alta X is the way to go. Thank you for that comment. I have heard numerous different things. Some people like them, some people don't. Either way, the point is none of these drones, by the way, come with my universal seal of approval. Like, well, if you couldn't tell, they do come with trade-offs. Trade-offs are tricky. So be very aware of that sort of thing. All right, where did my button go as I was coming out? Yeah, I don't like pilot-centric drones. I really prefer data-first drones that can fly and get the right data. Wingtra 1 is another really interesting one. This is a hybrid VTOL, takes off vertically, flies sideways. We fly it. This one's an interesting one. Swiss made. The data quality is exceptional, but it's just not as flexible as a multi-rotor. Quite frankly, I like in circumstances where we can use it, an M350 with an L2 is probably a better solution than this in most cases. Wingtra 1 is great if you regularly do very, very large projects, but there it runs up against certain regulatory barriers where the drone is more capable than the rules allow. It does have a LiDAR sensor, by the way, but interestingly, the Wingtra 1 is capable of being Blue List certified and being NDAA compliant, but the LiDAR sensor on it is not. So you can buy, again, it all depends. I used to have a slide like, how Chinese is your drone, right? The global economy, the global supply chain is incredibly interconnected. Every single one of these components has something that somewhere was probably made in China, right? Some of the steel might have been manufactured there. Maybe the motors are. Maybe some of the circuit boards are printed there. If it's running a top tier chip that was, you know, fabricated by TSMC, how does that play into the whole thing? So this is one of our more favorite non-DJI drones, but it's still, there's no way getting around it. It's expensive, difficult to use, and it really doesn't work on very small projects. So we have a handful of recommended aircraft. This goes a little bit beyond the LiDAR system, but DJI generally better. If you have to get around it, Wingtra is probably one of our favorite LiDAR ones, but it does come with a handful of caveats. GeoQ Group makes sensors that are really, really, really high quality sensors. I love the data that comes out of them. They are a pain in the butt to use. You better have some very, very smart people capable of processing their data because there's a lot of room for human error and things like the GeoQ Group drones, that sort of thing. And as we wrap this out, I should point out, we do help with hardware. We are our business, where we make our money, where we actually succeed, that comes from data processing. But we help with hardware too. So we're authorized resellers of a few pieces of hardware, but also we just give you free advice because at the end of the day, our goal is to help you get good data and process good data. So if you ever want help with hardware, if you're ever curious, call us, we can help. We'd love to give you at least some advice. We'd be happily would do that for free. So you buy a drone. Let's get out from hardware and talk about LiDAR versus photogrammetry. We already dove into the LiDAR basics quite a bit. So now let's talk about some photogrammetry basics so we can compare from a first principles perspective, which is actually better, LiDAR or photogrammetry, and when you can and should use each one or the other. So your photogrammetry basics. Photogrammetry, just by definition, is the science of making measurements from photographs. You take multiple photographs that overlap with one another, you find matching points in different photos, you stitch it together to create a 3D model out of the images. That means limitations. It only maps what it can see and identify from multiple angles. So it is based on vision. It looks at that. And the outputs then are both a 3D point cloud, much like a LiDAR system, as well as a 2D orthophoto. Those are the core outputs, and there are other derivatives, digital elevation models, that sort of thing, that are derivatives of orthophotos and point clouds in the process. But this is the standard process for modern digital aerial photogrammetry. And that has some benefits, meaning that it's really good in 2D. So this is a picture that I took from a data processing project of an actual photogrammetry derived point cloud on the left, not even the orthophoto, just the photogrammetry derived point cloud, and the raw LiDAR point cloud on the right. And you can see nothing there. And hilariously, that actually, I spent the time to make sure it was exactly the same place. This screenshot, even though it's just a bunch of invisible black dots. And while there are some things you can do in LiDAR, you can add colorization to the point cloud as part of the point cloud creation process. You can do that, but the 2D remains less accurate on LiDAR than it is on a photogrammetry point cloud. You can also use intensity, but intensity, I can tell you from doing a lot of LiDAR, aerial LiDAR, intensity is simply nowhere near as good at identifying 2D features as photogrammetry and imagery. So that is like one of the huge benefits. Even when you throw away the concept of cost, photogrammetry is just better with 2D features. Images like this are, from a LiDAR perspective, almost completely flat. But if you need to find paint striping for whatever reason, maybe you're doing an Alta survey, if you need paint striping, you really should be using photogrammetry. Same thing with some of these railroad tracks. Those will look completely flat, and depending on their reflectivity, the intensity scan might not even show any sort of difference there. Same thing, you can see some little ground control points here in the corner as well, but depending on your resolution. But seeing things like ground control points, 2D features, photogrammetry is simply better on 2D. LiDAR is better in vegetation. If you have job sites that might look like this or look like this with a lot of vegetation, LiDAR is simply better. It can actually penetrate. It can get good topo underneath. Whereas sites with either very sparse LiDAR, something like this, photogrammetry is probably still a better solution, even with a couple of trees and bushes here and there. And of course, anything that's a solid dirt site, completely graded. We have clients that are in southern Arizona and New Mexico. They have way less need for LiDAR. Sometimes they need LiDAR, but in general, when there's less vegetation, you just don't need it. LiDAR is very good at vegetation. This is what a LiDAR point cloud looks like, which is the false color one. The real color one is going to be photogrammetry. This is a profile view. As we get into LiDAR, I do a lot of profile views. But LiDAR is just better in vegetation. And the other really big one is LiDAR can map power lines. If you need to actually map power lines, you need LiDAR. It is absolutely good enough to measure the actual poles, the towers, the lines, the line sag, all of that. That is what LiDAR can really shine in. So if you're working with utilities, if you need to get your data processed into PLS CAD, for example, you basically need to have LiDAR collection data for things like that. So at the end of the day, you've seen this slide before. Photogrammetry and versus LiDAR, honestly, they're different tools and they need to be used differently. And to emphasize at the end, if you have a LiDAR drone and a LiDAR project, our preference is to create a flight plan that allows you to fly both simultaneously. It's one of the things that the DJI L2 is good at, and then some of the GeoQ Group ones can do it too if you get your flight operations correct. And your overlap and your flight altitude and your scan angles and camera angles and all of that right. But that's somewhat beside the point. Flying both of them is generally the best way to do it. And using a blended workflow of both photogrammetry and LiDAR data on the data processing side, that is the most successful way to do it. You use LiDAR where there is vegetation, and you use LiDAR for power lines. And if you don't need that, then you're probably better off getting it from photogrammetry. If you have an option to fly either a photogrammetry drone or a LiDAR drone, people will regularly pick the photogrammetry drone because it is more lightweight, it is smaller, it is easier to use. And the other thing that I always acknowledge, We work with a lot of commercial sites that are in somewhat populated areas sometimes. There are people around, whether they're just crossing the street or you might be flying to adjacent to someone else's home. If you're flying a DJI Mavic 3, or their naming conventions are weird, Mavic 3 Enterprise or Matrice 4E, which are the two kind of small foldable photogrammetry drones, once you get up to a couple hundred feet, those things are invisible. You can barely see them. You pretty much can't hear them, and they don't bother people. If you are flying a LiDAR drone of any manufacturer, it is loud, it is heavy, and anyone standing near it will stand. They will look up. They'll probably come and talk to you. We've never had any incidents where it's problematic, but it's just one of those things. It's so much easier to fly something that's just kind of unobtrusive. So find the right balance. The right balance is up to you and your company, and we'll talk more about that balance in part 2 of the webinar, which is going to be, again, on the business side of things. When does it make sense to use a jack-of-all-trades drone? When does it make sense to buy a second? How many survey crews? Who do you train? All of that stuff is going to be included in part 2 of the webinar. And part 3 of the series is going to be all about processing LiDAR data, but I didn't want to finish this first one without actually going over what the LiDAR processing workflow looks like from a high level. So we've only got about 15 minutes remaining, so I can't go into huge detail, but again, that's what the part 3 is going to be, is a lot more detail as well as live examples working through the actual data. So the LiDAR processing workflow from a very high level starts with point cloud creation. That means you start with your raw LiDAR data, your IMU, which is the sensor on board, GPS and ground data, ground control points, check shots, that sort of thing, to create an accurate geo-referenced and colorized point cloud. Your LAS file, that is the key output that you are looking for. From there, you actually need to go through point cloud classification, classifying that, because when it first comes out of the system, it is not going to be classified at all. But saying, all right, what is ground? What is vegetation? What is features? What is objects, buildings, power lines, and more? From there, a step that we recommend, but is not necessary, so to speak, and I'll talk about it in a little bit more, is rasterization, where you use your classified point cloud to create a rasterized surface model, which is a big important step when it comes to the actual usability of the product. And actually, there are some major accuracy benefits to rasterization as well, which we will cover shortly. Then through drafting and feature extraction, extracting all of the data that you need, curb lines, if you are doing power line assets, power poles, paint striping, actually starting to get it closer to a survey before making a final map. That's where you blend it with photogrammetry data, other sources, adding in your orthorectified imagery. There's a lot of work that can be done to actually create CAD-friendly orthorectified imagery from LiDAR data, supplementing it with LiDAR. That's a subject that we'll also be talking about later, is advanced orthophoto creation using a hybrid of different data sources and that sort of thing. And that's what actually gets you to your final map. So to go just a little bit more detail, point cloud creation, this is the first step. This is typically controlled by the payload manufacturer. So example with DJI, it's their LDR data format is proprietary. So you basically have to process it in their software, DJI Terra. Same thing with Wingtra, you have to process it through a Wingtra hub. And you typically have to go through that first point cloud creation through the whoever the payload integrator was. They're the ones that get to control this step. But this is one of the most important steps to the actual accuracy of your project. This is where your IMU, your GPS data, your camera data, and your ground control points come together. Make sure that each LiDAR swath aligns properly with the one before it. This is really a data science step mixed with a little bit of kind of GIS work and cartography and that sort of stuff. It's not, so this one is really technical, but it's what drives the accuracy. If you screw up your point cloud creation and have it off by 10 feet, that's probably from this step. And the challenge with this is, much like most things that involve GPS, there are so many different ways that you can set up a workflow. And there are a number of ways to do it right, but even more ways to do it wrong. And in fact, I actually recommend look back to one of my previous webinars that we did specifically on drone RTK and PPK workflows. It's just really tricky because there are so many different ways to do it. Whether you get an Opus solution and post-process that, whether you're processing against a CORS solution or a virtual reference station, or you have a local base station, but it's set up over an arbitrary point or a local point. How many ground control points do you have? Where are they distributed? Like, there's just so much going on here. And there are a lot of ways to do it right, but even more ways to do it wrong. So you got to be careful here. Then when you get to classification, and we'll cover all the softwares that we use in part 3 of the webinar, but the first and most important thing with point cloud classification is always to just ask, what classes do you actually need? Too many people, particularly businesses that don't actually work in survey, say, oh, as part of creating a point cloud, we will classify the point cloud for you. And that typically says one of two things. Either number one, they're using pure automated point cloud classification algorithms, which, while impressive, are typically not good enough for survey. Good for GIS work, by the way, when you're just using an automated filter it between buildings, trees, and ground. Those are typically good enough for GIS, but not good enough for survey. But also, this is a very costly step because it requires manual cleanup, so you shouldn't actually do more than you need. Most projects, especially if you're doing topo, you just classify between ground and non-ground. Often, the best way to do it is automatic classification with manual cleanup. Here are just some examples of what an algorithm might do as far as poorly classifying ground versus non-ground. It works. It is worth noting we have worked with every software out there, every attempt at AI and machine learning. And while they're getting better, there is no magic algorithm that works with everything. Many of them will help, but you typically need a good amount of manual cleanup after the fact. So you need to be able to understand how to set your bin size, your base angle, what type of vegetation it is, what type of slope you're working on, that sort of thing as settings to get your ground classifications. Once you get that, you get to rasterize your data from a point cloud into a raster grid. This is what a project might look like with vegetation from the imagery, and then a raster grid where you actually convert it into a high resolution rasterized digital terrain model. So why would we use that? Why not just the point cloud? Well, while it is not strictly speaking necessary to create a surface from raster data, good rasterization can smooth out noise and improve project accuracy. This is, as a data geek, one of my favorite slides because you can see a classified point cloud up top, a pretty high resolution rasterized surface here. This is a profile view, high resolution rasterized surface with a lot of peaks and valleys in the middle, and then a smoother one at the bottom. And the mathematics here are so fascinating because that surface on the bottom, that smoothed rasterized surface, is mathematically and statistically provably more accurate than the actual laser scanner point cloud itself. Because laser scanners do have noise, they have error in them, and that error is generally normally distributed. And if you average out the error to create a single smooth surface, you can make it better. But it requires a trained hand to be able to actually rasterize it in a proper way that smooths it without losing some of the definition that you want. How do you manage sharper features like peaks or valleys or curves or gutters and things like that? This is another one of those tricky things that on smooth terrain, this can really help, but it requires a trained hand to be able to actually smooth that out and create high quality data from it. And then, of course, you have to go through what is typically the most tedious but least magic part, which is just drafting and feature creation. Creating a tin surface, drawing your brake lines, your crown of roads, marking your manhole covers and your paint striping and all of that. And then you get it into your final map where you create your blended CAD-friendly ortho photo, merge photogrammetry and LiDAR data together. Keep clicking and hope that your PowerPoint doesn't freeze. There we go. Create your tin surface from all of it, apply custom layer templates, and put all of it get ready and package it for delivery. Because what I always like to say, when you go through all these steps, the end goal is a map. And the final survey should look the same, whether made conventionally with the drone. That's what this is about as we kind of start to wrap things up, is to create a final map out of all of it. And again, I mentioned this is all what we do. We work with surveyors who fly a drone, send us the data, you fly the drone, we process the data to actually create the exact deliverables that you need. Whether that's photogrammetry processing or LiDAR or PLS CAD or power line survey, that's what we did. That's what we do. And today we actually have another offer for you guys, which as we wrap things up and get to questions, if you are a new customer that's working with us, we basically have an offer to get you $500 off your first project. So if you want to process your data with Aerotas, we would love to process it for you. I will go ahead and put a link in the chat here, or you can scan that QR code. Basically, if you attended this webinar for the next 24 hours, we're keeping this link live to give you $500 off. Or if your project is under $500, we'll give it to you for free. So we would love to process your data and actually show you what all of that looks like. And so I'll keep this up on the screen for a minute as we now jump into the Q&A for the last couple minutes of time. Mike, I don't know if you have been looking through questions or any good ones. Let's see here. Yeah, things like, will the slide deck be available? Absolutely. Yes, you can.
Yeah, and also we have not cleared this with any state surveying boards, but we can absolutely provide a certificate of attendance to anybody who would like. You can go ahead and email support@aerotas.com. I'll throw it in the chat in case anybody would like a certificate of attendance. We will monitor that, monitor who's here. So obviously we'll send that out to anybody who requests it.
Yep. We've got some good hardware recommendations around everything. Oh, is ground control necessary when combining photos with LiDAR? Strictly speaking, it is not necessary, but we strongly, strongly, strongly recommend using LiDAR data or using ground control with LiDAR data as well as with photogrammetry. While you can rely on no ground control, if your GPS processing is very, very good and tight, you can get away with no ground control. Ground control, we think, is a really important part of any land surveying workflow for a number of reasons, not least of which is being able to catch errors. Especially the more complex systems that are out there, the likelihood that you just make a basic error is huge. And we've seen it before where someone even does an Opus solution on on their base station, and Opus just gave them something weird. If you've worked with Opus, you know there are a handful of things that can go wrong, and they'll reprocess the same data and say, wow, why did it change? And so ground control really helps you catch errors in the process. We consider them, they're not technically necessary. We think in order to be a professional surveyor, they are effectively required. That's at least our professional business there. Is there a benefit to flying a double grid mission compared with a single with more overlap? I would recommend you look in our library of webinars. Some of them are on YouTube, one about flight operations. Short answer is there are very few circumstances where a double grid mission will actually improve the data. There are a few, there are edge cases, but I'd say in about 98% of land surveying focused missions, a single lawnmower flight pattern is going to be better, not just good enough, but better than a double grid mission because there's a lot less data with it as well. Oh boy, thank you, by the way, for a number of good notes from some of our customers on here recommending both Aerotas processing. Yes, I always love seeing that. Let's see what else we got. Oh, this was a good question. What step in the LiDAR processing workflow can Aerotas take the data from with a yellow scan integration or a quantum cube, that sort of thing? So in general, if it uses a DJI system, we will take it raw, just straight off the drone, drag and drop everything, not even LAS format, just the raw photos and raw LAS files, because we have developed a very efficient, very good system for accurately processing DJI LiDAR data from different sources. For non-DJI drones, we typically start with the LAS file. It has to at least be an LAS file, even if it's not geo-referenced, because those steps are often controlled by the proprietary vendor and extraordinarily complex for that individual vendor, and there's just not enough volume for us to be able to buy each individual software and become proficient in those really, really complex ones. That's why I go back to that first step is typically controlled by the vendor. So if you have the more bespoke and complex the system, we probably start with an LAS file. Unless it's a DJI system, then we go from there. Oh, another question. Any recommendations on where to purchase reflective GCPs for LiDAR collection? Basically, well, you don't necessarily need reflective. Even reflective is hard because if you make it too reflective, the laser pulse bounces off and you can't see it. So you really want, we always like checkerboard patterns still. And Aerotas, we even sell online on our website. We sell ground control points. And we have ones that are bright pink and black. The pink washes out and the black absorbs the LiDAR. So you can usually see it pretty well in both a colorized point cloud and in a intensity-based point cloud, depending on your flight altitude and flight resolution. That usually works best. Some companies like using really big 3D ones, that sort of thing. So anyway, there are a bunch more questions, and we are out of time. I want to be respectful for your time. Thank you so much for joining us. And remember, you will get an email for parts 2 and 3 of this webinar as we go forward. If you have any other questions, drop them in the chat with your name, and we will follow up to help you with that. But anyway, thank you for joining us. I look forward to seeing you all again for parts 2 and 3, and I appreciate your time and attention today.